sure? Oh, great. What have you got? Yeah. Oh, is it wrong?
Yes, yeah.
You got, what are people getting for the B answer? And what did I say? What was the first derivative equal to? Negative 32. And the second derivative? So that's a negative and a negative, isn't it? Fallen and concave, whereas I said fallen and saddle. Okay, I'll change it, so it should be fallen and concave then. Circle this to change later, so this one should be fallen concave. Yeah.
Is your email just
Stephen at Stephen at the IFC.ie. So just that's the first part of it. Are you sending me the lab reports? Yeah, the plan. Okay, we'll continue now. Okay, guys, can we look up now? We'll continue. So, what we're looking at in the second class now this morning is optimization. Yep. So, optimization is a very important topic in calculus. Calculus is very important for many reasons, and one of the reasons calculus is so important is because of this topic, optimization. What's the meaning of the word optimization here? Ah, come on, you know optimize, don't you know this word? What's it mean? Do the best. Try not to use the word itself to explain the word. Yeah, so yes, true, optimize does mean optimize, but it also means the best or most efficient. Again, not using the word to explain itself, you know. Do you know that old English joke, like, what's a potato? You know, it's a potato. You know. Right, anyways, let's have a look at an example. So let's suppose, and this would be an exam type of question, you want to make a paper cup. So you want to make a cheap paper cup that holds, we'll make it hold 300 cubic centimeters of liquid. You know, so a cup like this. You want to make a paper cup like this. Okay? The way to make this as cheap as possible is to use as little paper as possible, right? I mean, the cost here is how much paper, how much cardboard was used. So what feature of this shape represents how much cardboard was used? Is it the volume? Is it the area? Is it the height? Is it the width? What is it about this that tells us how much cardboard was used? Which feature? It's the area. Yeah, the surface area of this corresponds to the cost, right? If you have twice the surface area, then that means you've used twice as much cardboard, which means the cost is doubled. So if we were to change this problem into a mathematical problem, what we want to do is find the minimum area. So step one is we have to change this into a mathematical problem. Yep? Okay, now, step two, let's calculate the area. So we'll call this H and R, and we're looking for H and R. So you'll need to know these formulas for the exam. The area here will be pi r squared h. That's the area for the circle on the base. And then what's the area for the curved part? Yeah, it's 2 pi or h. Now, these formulas you would have done in middle school, which probably seems like a long time ago. You'll need to brush up and re-memorize these area and volume formulas, okay? Because they're not in the formula book. Not in the formula book, I'm afraid. Okay, so the problem we have now is that there are two unknowns here. What are the two unknowns here? The R and the H. And this is a problem, because we only usually deal with one unknown, which we often call X. So we need to replace one of the unknowns. And the way we can do that, and again this is common in the exam, is we have to use another equation. So what other equation could I use here? What other piece? The volume one, yeah. What is the volume? It's 300. I tell you at the beginning, I want my cup to hold 300 cubic centimeters. And the formula for the volume of a cylinder is pi, you're thinking of a cone, pi r squared h. Now, you have to think very carefully which will be easier going forward, to get the h here and sub the h back, or to get the or here and sub the or back. Yeah, why? No square root unnecessary. So that gives us h equals 300 over pi r squared. And then with that, we sub it back in here. So now we have area equals pi r squared 300. Is that right? Over pi r squared plus 2 pi r 300 over pi r squared. Yeah? Okay. We can do a lot of cancelling. What are we left with here? 300 plus 600 over or. Yeah? Now, this is like y equals 300 plus 600 over x. You know? Or is the variable, the unknown, and a is the thing you want the minimum of. Just like the y. So, what should be my next step now if I'm looking to make the minimum a for some value of or? Differentiate. So, let's do that now. dA, dr. No, something's gone fishy. I've made some mistake and nobody.
Area. It's 2 pi r squared.
What? This one? Oh.
2 pi.
Shh. Sorry. I need to brush up on my middle school maths, it would seem. Yeah, there's no h in the formula here, thank you. So that means I didn't have to replace the h here, doesn't it? Ugh. No, pi r squared. 2 is if we had a top. There's no top on this cylinder. There. No, I'll just clean this up. My spider senses were telling me something was wrong here. Pi r squared. Right. So, what's the derivative of pi r squared? 2 pi r, thank you. 2 pi r. I don't need to write this. Just make some space. Okay, so what do I do next now that I have the derivative? What's next? Sorry, dA, dr, thank you. What do I do now that I have the derivative? What's wrong? Huh?
Negative 1,200.
We have all sorts.
Oh, I got. Right. A equals pi or squared. The pi's cancel.
And R.
So, now I understand what you're saying. Sorry. I haven't done the derivative yet.
Yes.
Okay, so when you were saying I haven't done the derivative yet, you meant I haven't done the derivative yet. I understand now. Okay. dA dr equals 2 pi r minus 600 over r squared. And this should equal 0. Yes. Right? Now, what's the easiest way to solve this? What should I be doing next? No, before that. I could multiply by r squared, or I could just take this over to the right, and then I have 2 pi r equals 600 over r squared. Next. Cross multiply. So I get r cubed equals 600 over 2 pi. So, finally, r equals, if you cube root this, what do we get, please? Something for sure. Something about this big, I would say. 9 centimeters would be like, so that'd be an 18 centimeter radius cup. So, what is it, 4.57?
Yes.
That sounds a bit more believable as a radius for a cup, doesn't it? And then how can I get the h? I need someone to sub this back in earlier to here. And I have my h now, please. 300 over pi times 4.57 squared. It's about the same, isn't it? Okay, fine. 4.57. So this is actually interesting because it tells me, are you sure? 300 over pi r squared? Also 4.57? Okay. So obviously this cup is not 4.57 centimeters tall. So that means I could make this cup cheaper, but I would have to make it shorter. And I probably would have to make it wider. How wide is this one? Who's got a ruler? Let's see, roughly 4.57 times 2 is 9 and a bit, isn't it? Yeah, so this is only 8 centimeters. So you could make this cup cheaper if you made it a little bit wider and a bit shorter. However, this feels a little bit unnatural to the user, right? Even though it's cheaper. So I think, you know when you see those small cartons that are quite shallow and quite wide, like for noodles or something like this, this is probably the optimum size. And it doesn't really matter what shape that is, because you're not walking around with your noodles in your hand. Do you know what I mean? Whereas with a coffee cup, you kind of are limited to the person's hand. Okay. So yes, all right. This has taught us that coffee cups could be made cheaper, but people don't want short, wide coffee cups. Okay. Now we'll do another example, and this was an exam example. We'll do another one now, and we'll keep with the theme of coffee, anyways.
Teacher,
Yeah.
why do we equals the derivative to 0?
Oh, Carul, you know the reason why. Why do we make the derivative equal to 0? Who can tell him? Yeah, and what are we trying to find? Why do we make the derivative equal to 0? Oh, come on, guys. OMG. Why do we make it equal to 0? Oh, guys, come on. We make it equal to 0 because we're looking for the turning point. We're just about to say it. Yeah, okay, fine. Fine. Right, well, let's have a look at another example. Can I scroll down? Yeah. No? What?
I mean,
You're not going to ask me what's the turning point, are you?
I don't know. What's the relation between the turning point and but I mean,
So remember we wanted the minimum area.
oh,
And turning points mean minimums.
yes. So we
It's
are
such a-
finding the minimum
Yeah.
surface area.
Yeah. We get it. Good. All right, satisfying. Okay, can I scroll down? Yeah. I want to make a realistic example now. They had this example in the exam maybe 4 years ago, a business example of optimization. Okay. So I don't know. We'll keep it with coffee cups. So let's see. Yeah, I'll just change the numbers a little bit. So. No, I'll keep the numbers the same because they're reasonable numbers. So in question 4, when the price of coffee is €2, then the demand is 100. So that means when the price is 2, then the number of customers in the day will be 100. Now, what do you think would happen if I was to drop the price all the way down to, say, €1? Yeah. Yeah, but what would you expect the Q would do? Not necessarily double, but still increase. And in this particular example, I say that the Q is 150. Okay? So are we all happy with the concept? You lower the price, you get more customers. Fair enough? Yeah. Okay. The shop has what's called a fixed cost. So this is the cost the shop has to pay every day, no matter what. So for my example, I say a cost of €70. Now, what would be an example of a fixed cost for a coffee shop? Not really, because the shop isn't opened, then... No, if it doesn't buy any cup. Rent. Rent would be a fixed cost. Whether they open or not, they're paying €70 rent, for example. Or maybe insurance. They might have to pay the workers if they're on a fixed salary. Yeah. So anyways, we understand that there's some costs that they can't avoid even if they don't open. Okay, so that's a fixed cost. Okay. This cost must be paid. But there's also something called a variable cost. And this is 33 cents. And this variable cost is for each cup of coffee. So obviously when they make a cup of coffee, they have to pay the person's salary, they have to pay for the milk, they have to pay for the coffee beans, and so on. So roughly they say, okay, each cup of coffee we make costs us 33 cents. Yeah? We get the idea for this one? Yeah? So for example, if they make 10 cups of coffee, how much would that cost them? $3.30. It's actually worse than that because they had to pay the 70 as well. So if they only opened and made 10 cups of coffee, that would cost them €73.30. So they would have to charge a lot for those 10 cups of coffee, right? Yeah. Okay. The first question is, I want a formula for Q. Let's put this on a graph here. Q and P. When P is 1, Q is, what did we say? 150. And when P is 2, Q is 100. So the graph is, sorry, it's goes from 150 to 100 going down. Now going down makes sense because as the price increases, the quantity sold per day decreases. I mean, this is fairly obvious. Okay? How could we get the formula here? Well, what relationship is this? It's linear. So we know that Q equals MP plus C. Let's get the M first. So what's the formula? It'd be Q2 minus Q1 over P2 minus P1. So what would that be here?
25.
It would be 150 minus 100 over 1 minus 2. Minus 50. So I have Q equals minus 50P plus C. And how can I get the C? Sub in a point. Let's just sub in this point. 150 equals minus 50 times 1 plus C. So C equals 200. So we have the first part done. Q equals minus 50P plus 200. Now, let's have a look at what this result means. If the coffee was free, how many would I sell? Look at the formula. If the coffee was free, how many would I sell? 200. Why? What did you do?
0.
Put P as 0. I would sell 200. At what price would I sell no coffee?
4.
At 4 euros. 4 euros for an Americano? Yeah, I probably won't sell any of those. Right? Okay, so it seems reasonable, the formula. Although perhaps it's a little bit unreasonable when the price is 0. You might say, if the price was 0, then maybe it'll be 1,000. You know, so it's not great for when the price is 0, but that's not really ever going to happen. Okay? Can I scroll down? Okay, next, find a formula for the total cost. Total cost is your fixed cost plus, what's the other type of cost we had? Variable cost. Okay. How much is our fixed cost? Our rent? 70. And our variable cost is 33 cents, but that's for each cup of coffee we sell. So in total, what would it be? Yeah. Multiply by? Not quite. By Q. How many we sold, the quantity. Yeah? But if you look at the question, I say give my formula in terms of P. So what do I do next if I want it in terms of P? Substitute it in. Very good. Okay. This would be 70. If we expand that, what's that? Minus 0.33 times 50. 16.5 exact. And then 0.33, what's that, 66? Yeah? So total cost is equal to, yeah, is this okay? So let's consider our two scenarios again. When we sell the coffee for free, what's our total cost? 136. We have to pay the 70 euros rent and then all those costs for all those cups of coffee. What happens if we put in the price as 4 euros? What do we get here for the total cost? Why do I get 70? I thought it was 70.
So you get 1.
If you put P as 4.
You get 66 on this minus 66.
Huh? 136 minus 16.5 times 4? 70. Oh yeah, so 136 minus 66 is 70. Okay, fine. We're all talking the same thing. Why did I get 70 though? If you think about it.
Because we get money from the coffee, which we use.
No, we got no money from the coffee. Remember we said earlier, if the price is 4, how many cups of coffee do we sell? 0. So it's like we made no cups of coffee, So the only bill we have to pay for the day is
Rent.
our rent, our fixed costs. Because we didn't make any cups of coffee. It was like we were shut. You know, selling no coffee cups is the same as being shut, right? Okay. All right, part C. Let's get a formula for total revenue. Total revenue means total sales, total money we took in. So, how much are we charging per cup of coffee? That's P. And how many cups of coffee did we sell? Q. And let's sub in the Q again. What did we say it was? Minus 50 P plus 200. So that's minus, let's put it in red again. Total revenue is minus 50p squared plus 200p. What's my revenue if my coffee is sold for free? Total revenue? Zero. And if you put in p is 4, I would hope you would get 0 again. Because remember we said when the price is 4, we make no sales. It's 0, yeah. So the formulas are making sense. They're all working so far. Okay. D. So does the company care about the sales? Not really. Does it care about the cost? Not really. What it ultimately cares about is the profit. The profit, yeah. So what would be the profit here?
0.67.
It would be what minus what?
TR minus
Very good. TR minus
TC.
TC. Okay. What did we say the formula was earlier for TC? 136 minus 16.5 P. Okay, so that would be minus 50 P squared, right? Plus 216.5 P minus 136.
Yeah.
Minus. Yeah? That's profit. Now, what would the company like to do with its profit? Maximize it, wouldn't it?
Yes.
Not minimize it, right?
No.
Maximize it. So, how can we get the maximum profit now? What should we do? Derivative equals 0. So, what's the derivative here?
Minus 100
Yeah?
plus 216.5
Equals 0. So that means P should equal €2 and 16.5 cents. So the price should roughly be 2.17. Now let's confirm we found the maximum and not something stupid like the minimum profit. How can we confirm we have a maximum?
second derivative.
Yeah, so if we differentiate again, we get minus 100. Well, that's it, just minus 100 if we differentiate again, which is less than 0, which is therefore maximum. So we can make the most profit when the price is equal to €2.17. Now this is very interesting if you think about it. Let's imagine the coffee shop was selling coffee at €2.50, 50. What would happen to its profits if it dropped the price from 250 to 217? What would happen to its profits? It would increase. It would increase. Because we just said that this price gives us the most profit. So 250 was overcharging. There were customers they were losing that they could have got. By lowering the price, it is true they get less money per customer, but the extra customers that they get more than cancels out the loss from the cheaper coffee.
So is this like a global max?
It's a global max. And we know it's global because this guy here is quadratic. And quadratic functions have global max. Which is interesting. Okay? So my point is, this is why sometimes you would see things go on sale. Because even though they drop the price, if they can get in more customers, they can cancel out the less money they have per sale. Yeah? Okay. I just let you try these in a minute, but I just want to give you, I won't do a calculation, but I just want to give you one more example that's similar to this. This was in the exam a few years ago. It wasn't cups of coffee, it was DVDs, if you even know what a DVD is. But it was all the same steps, okay? They had the same, it was a DVD store selling DVDs, and you had a fixed cost, and there was a variable cost per DVD, and so on and so on. The story's not important, it was the same steps, okay? So, the other example I can think of is with tax, which I always think this one is interesting. This is the total tax that the government gets from its people, and this is the percentage tax it charges to its people. Okay? So, if the government charges 0% tax, then how much tax will the government take? It will get 0. And if the government charges 100% tax, how much? Yeah, how much will it get? No. How much will it get? It will get 0. Why will it get 0? Well, I'm sorry to tell you this. If I was paying 100% tax on my salary, I wouldn't be here. And so if you charge 100% tax, then yes, you would get nothing, because what's the incentive for anybody to work if all their money is lost, right? So this point here is 0. If I connect these 2 points, it means that there is some point in the middle between 0 and 100% that gives the government the most tax. And if it charges more than this, a bit like with my coffee example, does it get more or less tax from the people? Less, you know. So in some situations, if the government is overtaxing, it can actually get money in if it lowers the tax rate. Okay. The only example I can think of is Russia in the 1990s lowered its percent tax rate, and it saw its revenue increase. I can't think of any other examples of this, but the point is the same as the coffee example. You can pass the optimum, and you have to lower to actually go back to the optimum. This does happen. Okay. So I haven't seen this in the exam, but it's an example that I could imagine in the exam as well. Now these questions are quite tricky in the exam. The calculus questions in the exam comes in 2 types. The first type is what we did this morning with the general derivative, and the second type are these optimization. Yeah. So this gives you a 50-50 chance in the exam. You can get an optimization calculus question, or you can get a general derivative question. Obviously, well, I don't know. Obviously, I think this one is easier, general derivative. Okay, optimization is much harder. But again, it's personal preference. Okay. I do need you to do all of these because they're hard, and because they're all different, and it's a different story each time. Yeah. It's practical problems. Yeah. What I always find interesting with students is they always moan, well, maths is not useful, maths is not useful for anything. And then when you get practical problems, it's well, I don't want to do practical problems. Okay, so all the questions on page 78, please.